Welcome to Dr. PT's Chemistry Essentials, A-level chemistry made easy. In this video, we're really going to focus in on what we call Friedel-Crafts reactions. And this is going to involve the electrophilic substitution mechanism. And if you haven't already, go back and watch the video on the electrophilic substitution reactions of nitration and halogenation, because that'll give you a grounding for what you need to know for today. Now, Friedel-Crafts acylation involves two different types. We've got the use of acyl chlorides and the use of haloalkanes, and we're going to be exploring all those going forward. Now, in the previous video, we've been looking at benzene and its reactions by the process of electrophilic substitution. And it's really important, we've already spoke about the fact that this mechanism is substitution, which is very different from alkenes, which undergo electrophilic addition. Now, before we focus on these two new transformations, I'd like you to pause the video and come up with the reagents and conditions for each three of these arrows leading from benzene. Okay, so for nitration, you should have got these as the reagents and conditions. Remembering the 50 degrees is for mononitration. If you increase the temperature here, you'd get multiple substitution and more nitro groups on your benzene ring. For bromination, we use the halogen bromine and the corresponding halogen carriers, either iron tribromide or you can choose aluminium tribromide. And then chlorination should be very similar, but switching these out with chlorine. Now, with these two new transformations shown on this concept map, you'll notice that the actual bonds are made between the carbon of the benzene to a carbon elsewhere. And this is called a carbon-carbon bond forming reaction. And these four types of reactions are particularly useful because lots of drug molecules and biologically active molecules, as well as other molecules, have carbon-carbon skeletons or backbones in. So it's really important to be able to make these new connections. And usually a carbon-carbon bond is unreactive, so it's quite difficult to make. So any methods that we can do and use to create these carbon-carbon bonds is good. Now, just as a side note, just so that we're all on the same page, the R group in organic chemistry stands for basically rest of the molecule, and it's any group of carbon or hydrogen atoms. So it could, for example, be a methyl group with one carbon. It could be an ethyl group with two carbons, and so forth. Now, collectively, we call these carbon-carbon bond-forming reactions with benzene Friedel-Crafts reactions. This one is called a Friedel-Crafts Acylation. Whereas on this particular transformation, we've introduced a carbonyl group with a CH group attached to it. So this collectively is called an acyl group. And so on the introduction of this is called a Friedel-Crafts Acylation. So really subtle difference in the word between alkylation and acylation, but an alkyl group is just without carbonyl, whereas an acyl group has this carbonyl C double bond O group. Now, in order to introduce this R group, and let's for just simplicity say that this is a methyl group, then we need an electrophile with this methyl group in it. And that electrophile is a haloalkane. So this is going to be our alkane part of it, and the halogen is usually chlorine. So there's our alkane, and then we're just going to add a halogen to it. So there we've got chloromethane. And then because we've got that chlorine in there, we're going to have to remove this to make this our electrophile. And we're going to remove that through the use of a halogen carrier. And so this halogen carrier, aluminium trichloride, shares the same halogen as we've got in our actual haloalkane. Now, you'll remember it is a substitution reaction, so we can see the hydrogen here is being substituted by this methyl group, and so this comes away from the benzene, and the chlorine here also is removed from the haloalkane, and so that combines with this hydrogen. So you get the newly substituted carbon-carbon bond formed plus a byproduct of HCl. Now, very similar, to introduce the acyl group, Friedel-Crafts acylation needs to add in this whole group here, so the carbonyl and the R group. Now, once again, just so that we're looking at an actual example, we're going to change this R group for the methyl group. So all I've done is translate this across into my actual reagent. And then this isn't a molecule itself. That carbon only has 3 bonds around it. Its 4th bond, to ensure it has a full outer shell, is to chlorine. And that's drawn there. And once again, because whenever you have a halogen in one of your reagents, you always need a halogen carrier paired with it. So we're going to use aluminium trichloride. And this is an important thing to remember in all of these examples, is that if one of the reactants contains a halogen in it, then you're going to have a halogen carrier of the same halogen. And finally, just to complete this, if we're doing an acylation, this chlorine is going to combine with the substituted hydrogen, so you also get a byproduct of HCl, just like you do with the alkylation. So let's just strip this diagram back, so we're just focusing in on the Friedel-Crafts Acylation and acylation. So you can see clearly the pattern is whatever the actual R group is on the benzene ring attached to it, you just add a chlorine to it. So if I was to swap this one for propyl, then the corresponding haloalkane that would be needed to be used with a halogen carrier would then have to contain this actual propyl molecule as part of the alkane. And exactly the same process is happening for this acylation. You've always just got to match this part of the molecule, the benzene molecule, to this. So you can see it's all about pattern recognition. But it can be quite difficult because they can substitute the benzene that you're looking at. And obviously in the exam, it will all be in black ink. And you just need to be able to identify the change that has occurred and match it up with the transformation. My recommendation would be every time you meet a new transformation, that you add it to a flashcard, learn the generic transformation and the pattern of the reagents and conditions, and then that will allow you later on down the line to be applying it to any exam situation, any new novel situation. So before we go and have a look at the mechanism of Friedel-Crafts Alkylation and acylation, I want you to just pause the video here and see if you can answer this multiple choice question on this topic area. Okay, so if you've had a go at this, I hope that you have chose C as your answer. The reason being is if we have a look here at our molecule, we've obviously introduced this acyl group here. And what we know is from the previous information that we've just looked at, we always need a acyl chloride reacting with a halogen carrier. So the big giveaway here is that all the other molecules don't actually contain that acyl chloride because it needs the atom chlorine in. But just for completeness, if we think about exactly what this acyl chloride is going to look like, then you just look at the thing that you've introduced. The carbonyl is directly attached to here. That's our CC bond. So we take this motif out. We know carbon only has 3 bonds when we've abstracted that from our structure. So we need to put that 4th bond to chlorine. And there you have your acyl chloride. And what you'd expect, although obviously not needed for this, is the byproduct would be HCl. So we're going to focus in now on the actual mechanisms and how to draw them. They all will follow the generic transformation of electrophilic substitution. We've looked at this in the previous video on nitration and chlorination. So I want you to just pause the video here and see if you can fill in the curly arrows and the intermediate for this transformation shown with this generic electrophile E. Okay, so this is the mechanism that you should get. A curly arrow from the ring going to the electrophile because the electrons are high density here, so this is where they originate from. And the double-headed arrow tells us where that pair of electrons actually goes towards. So then we're forming a new bond at this carbon here to this electrophile in our intermediate. Now you'll notice that by looking at the actual product, I knew it was that carbon that formed the electrophile bond. Also, what's worth noting is this is a skeletal diagram, so none of the hydrogens are shown. But in the next step, we're going to need to show the hydrogen here. And also on forming this new bond in this process, we've actually disrupted the delocalized ring of benzene, and it's going to extend only from this carbon down to this carbon, leaving this carbon out. And because electrons have left the ring, so this ring is now electron deficient, it doesn't have enough electrons, so we show that with a positive charge. And obviously now looking at our product, we need to close this ring up because benzene really likes the stability of this delocalized ring, so it's going to reform that. And so in order to do so, it needs new electrons to close this gap. Now those electrons come from this sigma bond, so this single bond between carbon and hydrogen. And the two electrons that are involved in this covalent bond basically fall back into the ring, letting hydrogen drift away because it's no longer connected. You can see the double-headed arrow goes into the ring to show that the ring's been formed. This bond no longer has any electrons in it, so this hydrogen is going to just come on the side, and itself is now positively charged. It will combine with whatever has allowed the electrophile to form, and that will make more sense when we look at the mechanisms for alkylation and acylation next. Now if we just take this same skeleton system as above up here, but for the alkylation we're just going to swap E plus to be the positive alkyl group, and in this case we're just going to look at the alkyl group of ethyl. The reason this acts as an electrophile is because this carbon here only has 3 bonds around it. It needs 4, so it's electron deficient, it doesn't have enough electrons, so this carbon here is the area where the positive charge is. And so the same mechanism as above happens. Now, in order to understand how this electrophile forms in the reaction, we need to look at where it's come from. So the electrophile itself is this part, the alkane part, plus the halogen, this time chlorine. This then reacts, this haloalkane then reacts with the aluminium trichloride halogen carrier. And what actually happens is this aluminium trichloride takes this chlorine, breaking this bond, leaving our electrophile and aluminium tetrachloride behind. And so you can see we've formed our electrophile that then undergoes the transformation with benzene. Just so you can see what's going on here, in grey, I'm just going to show you the small mechanism underneath. You don't need to memorize this, but it might help with your understanding. So aluminium has space for some electrons, so this bond breaks, so the two electrons in this bond move over to here. So you've got to imagine this is now broken and we've formed a new bond between the chlorine and the aluminium. And we're left with these two products here that are exactly the same as above, just shown in a slightly different way. Now, just like in halogenation, so in bromination and chlorination, the halogen carrier is always regenerated. So here it's been changed into this aluminium tetrachloride, but we are going to have to do another process to get it back to this because it's catalytic, so it's not used up in the reaction. So what happens is the aluminium tetrachloride reacts with this H plus that's given off, which then produces aluminium trichloride and HCl. And it's this HCl that gives you your byproduct in the overall transformation. And so the overall transformation, taking all these little mechanistic parts together, will be as followed for this reaction. And so you've got the aromatic benzene ring, you've got the haloalkane that obviously has to generate an electrophile, and it does this by reacting with the halogen carrier that is required. These then combine via this mechanism to produce this product, and on substitution of the hydrogen for the actual alkyl group, you end up with HCl as the byproduct. So the mechanism for acylation is pretty much identical, so we're going to follow the same procedure and look at how that works with acylation. So with this acylation, we're going to be introducing a acyl group which collectively has 2 carbons in it. The first carbon is the actual carbonyl carbon, and then the second carbon is the methyl carbon attached to this. So working backwards, that means our intermediate looks like this, and the bond that's formed between the benzene and this carbon means our electrophile must look like this. And here, obviously, carbon had 4 bonds around it. We've just broke this bond. It only has 3 now, so it's going to have a positive charge, which therefore makes it that electrophile that's required to react with the electron-dense delocalized ring. So we need to think backwards. This was an acyl chloride, and so our electrophile generation is going to require the acyl chloride version of this. So we're just going to add in a chlorine group to this. Hopefully you can see this part is that part. We've just added that chlorine in. This is now an acyl chloride. This reacts with the aluminium trichloride. Once again, the aluminium trichloride works by actually abstracting or taking off this chlorine, breaking this bond. So the chlorine goes over to the aluminium trichloride to form aluminium tetrachloride. With this bond broken, this carbon only has 3 bonds around it, so it's positively charged and is so therefore an electrophile. And then what happens is, just like before, the aluminium tetrachloride needs to regenerate the catalytic aluminium trichloride, and that's what's happening in this regeneration step. So our overall reaction scheme looks like this, and you can see how these different components fit in with the actual mechanism that has been suggested for the formation of this product. Okay, so trying to put all of this into practice, with this particular snippet from an exam question, what I'd like you to do is, in this box here, come up with the reactant that needs to react with benzene. Remind yourselves of the conditions that are required for this, and then something extra is to then draw the mechanism combining the reactants together to form this product. Now, obviously, in this structure here, we have calculated structure, but for the mechanism, what I want you to use is the delocalized structure, as this would be the one that would be given in an exam if you were asked to draw the mechanism for something. So pause the video now and have a go. Okay, for part 1, looking at what it is that you're reacting with benzene, you can see this is the new carbon-carbon bond. So in your mind's eye, you need to almost split this into 2. And this is going to be, the one on the right is going to be the part of the reactant, and the one on the left is our benzene molecule. So let's just draw out what remains here. So splitting that bond, we've got a carbon up, and that carbon there, being that carbon there, is next to us another carbon and then another carbon. So we're going to just flick that off there. Now again, this carbon only has 1, 2, 3 bonds around it. So we need to draw in that 4th one. And you need to remember this. This transformation uses an acyl chloride. So we're just going to put a chlorine in there. Now with that, we need the conditions. That conditions includes a halogen carrier. So because we've got a chlorine here, we're going to use aluminium trichloride. Then really the complicated bit is the mechanism. And this would usually be worth about 4 marks. So we're going to just specifically go through it. I've asked you to show generation of the electrophile. So the electrophile here, if we look at acyl chloride, the electrophile is taking this chlorine away and drawing what remains and putting a positive charge where that chlorine was bonded to that carbon. So this carbon here is going to be positive charge. It's almost the reverse of the process that we were doing here. So we had to add on a chlorine here. We're going backwards and we're looking at this part here. And so you can see we've got that bit there, which is this bit here. And we've just put a positive charge where that once was bonded to chlorine. Now this doesn't spontaneously happen. That's why we have the halogen carrier. So we're going to have to add this to our scheme. And with that AlCl3 obtaining this chlorine, our byproduct is AlCl4 minus. So then that electrophile reacts with the benzene in our second step of the mechanism. So here we take benzene, we react it with our electrophile, which is what we've generated up here. The curly arrow goes from the ring, makes a bond to there. So this is that new bond that is shown in the structure here. We broke the delocalized ring in this step, so we're going to just have to draw this around from this carbon here to this carbon. That's partially charged now, so we put a positive charge. And then in our next step, what we're going to do is substitute the hydrogen that wasn't shown here because it was a skeletal diagram, but you've got it here. This is then going to fold into the ring, this bond, in order to regenerate the delocalized ring. And so hydrogen will come away from there, leaving our structure. And just to really highlight again, that's our we have formed. And here we know that that hydrogen has come away as H+. Some people will just put plus HCl here, but we're just going to show how this makes HCl in this third step. So the H+ reacts with the aluminium tetrachloride up here. And if we draw that, what happens is we reform the aluminium trichloride and then we get HCl. So that is why we've got HCl here as our byproduct. So in this video, we've been looking at Friedel-Crafts reactions using haloalkanes and acyl chlorides, undergoing electrophilic substitution. And that brings, with the other video on nitration and the halogenation of benzene, all of the reactivity that aromatic compounds do. Now in the next videos, we're going to be looking at phenol and directing groups. But if you found this video really useful, make sure you like it and then make sure you subscribe to the channel for new videos as and when they're uploaded.